nanocoulomb, and then you got like, no, this is positive down here. And then you got a negative and a negative and a negative, okay? And you want to find the value of the electric field. So, fields are very much like a quintessential example of vector quantities, okay? Because they have magnitude and they have directions. So, remember, when you look at what's going to happen with an electric field, you look at the influence of what a positive test charge would be subjected to if it was placed at that location, okay? Obviously, a neutral particle won't do anything because it won't be affected by an electric field. So, oh, that's positive or negative. Oh, kind of upbeat people, let's choose a positive, okay? So the idea being on number 4 is that you're going to come in here and go, okay, I want to figure out what's happening, the net electric field at that point. Now, I'm not trying to calculate the force that this thing is going to feel. And here's the difference. To calculate a force, I'd have to have K, Q1, Q2 over distance squared, okay? So here's the deal. I can't calculate the force that this thing is going to feel right here at this point because I don't know what this is, okay? I don't know if this is a positive charge. I don't know if it is positive. I don't know if it's 1 nanocoulomb, 10 nanocoulombs, 20 nanocoulombs. I don't know, okay? This is why I can't calculate the force at this point. But what I can do is I can figure out the field, the net field of what that's going to be. Then later on, if I know the charge, then I can go, oh, well, the force that it's going to feel is that electric field, which is in nanos per coulomb, multiplied by the value of the charge, and then I'm going to know what it's going to experience once I actually put in the value of the force. So that's analogous to, hey, we've got a gravitational field. Well, what does something weigh? Well, I don't know what something's going to weigh. Excuse me.
Bless you.
Until I know what the mass is. So if I've got Hank the bowling ball in this gravitational field, right, and I let go of it, that's going to be a completely different value of force that Hank the bowling ball is going to feel versus Gary the golf ball. Okay? They're both in this gravitational field, but they're going to feel completely different forces. So somewhat the analogy is if you look at little g equaling big G m over r squared, well, if you look at the calculation of little g, that's independent of the mass. Everything is going to accelerate at the same rate. They're not going to feel the same forces, but everything's going to accelerate at the same rate. So that's what we're trying to find when we find the value of this electric field. Okay, we're saying, okay, at this point, this is what this electric field is going to be. Then once I know what the force, what that charged particle is, if I put it in that place, then I could say, oh, this is what that is going to experience. Okay? So all you're finding with this electric field is going to say, okay, it's there. This is the net effect of it. Then if we, later on, if we wanted to, if we knew what that charge was, then we could say, oh, this is what this will feel. So this is why you kind of look at this schematically first. So if this is this electric field and you assume that you have a positive test charge, oh, it's going to be pulled this way towards this negative, and it's going to be pulled this way towards that one. Those are going to cancel each other out. Okay, so you can calculate them, but they're just going to cancel each other out because they're going to be in opposite directions. But then you run into, okay, well, if this is a positive charge here, it's going to be pushed this way because of this is a negatively charged particle, and then it's also going to be pushed in that direction because of the fact that you have a positive charge down there in the bottom. So because of the fact that it's right in the middle, and you have a half and you have a half, and whether or not you do smash mouth physics or you get clever and you go, oh, that's 1/2 squared plus 1/2 squared and the square root of all of that, okay, but then that whole thing gets squared because E equals KQ over D squared. And then you just have basically 1/4 plus 1/4, you get a half, that's down there at the bottom. So it's just a matter of how clever you want to get with the algebra, okay? But anyway, so what you should see on part 4 is that your force is 36, and it's going to go at a 45-degree angle, okay? Excuse me, your electric field is 36 nanos per coulomb. So then you're going to drop that E field in there, get a reading of it. You're going to calculate the experimental error. Remember, that's theoretical minus experimental divided by theoretical. So basically, it's going to be 36 minus what you get divided by 36. Okay, there you go. Now, here's the difference of what's going to happen on part 5. So on part 5, now you're going to be talking about forces. So you got a negative 2q down here, you got a positive 3q up here, and then you've got a positive charge that you're going to drop up here. Okay? So with this one, this is going to get pulled in this direction, okay? And then in this one, you can actually calculate the force, okay? Because of the fact that you know the charge on this one, and you know the charge on this one, and you know how far apart they are. So that's the difference between 4 and 5. On 4, I couldn't calculate the force because I don't know the charge of what was in the middle. But this one, I can actually calculate the force because I know the forces that are involved on each charge. And then this one is going to push this one out. So there's a couple of ways you can look at this schematically. One option is you come in and say, well, if you like the tip-to-tail method, okay, so here's this force, and then this force is going to be coming down like this, okay, and then you're going to find the resultant, okay. Now, that would work out swell if this was a 90-degree angle, okay, but it's not, okay, because you have 60-degree angles, okay, doesn't work out. But at the end of the day, here's the only way that you can really work this problem, is to come in and say, okay, here's this x component, and here's this y component, and then here's this x component, and here's this y component, okay? Now, obviously, your x components are both going to have the same sign, because they're both going in the same directions. Your y components are going to be in opposite sides, okay? So when you look at it this way, if this was an equilateral triangle and all the charges were the same, then that they were the same magnitude, this would be an easier calculation to do because of the fact that, well, if everything was the same and all the charges were the same, basically your y components would exactly cancel out and you just have to find the x components and add them together. But because of the fact that we're not an equilateral, it's not the same in terms of charge, you have to actually go through and find those. So what you should see, when you find your x components, okay, the sum of your x components obviously has to be bigger than the sum of your y components because both your x components are going in the same direction. So if all goes well, your magnitude of your force on number 5 should be something times 10 to the negative 8th, and your angle should be between 90 and 180 degrees, closer to 180, okay? A lot closer to 180 than it is to 90. And you can kind of schematically, if you just kind of get an idea of the magnitude of those vectors, you can kind of see how that deal would play out. Okay. Anything else you want me to go over on the lab? Make sure that you have one graph that you had to draw, okay? So make sure that gets stapled to the back, and then go ahead and hand that in.
Well, I didn't get right. Didn't even get the angle yet. Yeah, part 5 I got 90 to the negative 8.
It should be 2 times 10 to the negative 8.
Which is not what I got.
What did he say the force was?
He said it was
Something to the power of
else.
negative 8.
What did you get?
9 to the negative 9th.
I guess I was doing.
That's what you
She
got.
probably made the same mistake as me. I don't know what the mistake was, but
And that's what he got too.
I got the right. So
It was
I
something
checked
to
with
be
her.
a negative 8.
I got the right angle with him, so I like the likelihood that I don't have the right answer. My answer is at very least proportional to the right answer.
Part 5, number 4, he said it was something times 10 to the negative 8.
On number 5?
Yeah, part 4.
Yeah.
Or, wait, part 5,
Part
number
5
4.
was something times 10 to the negative, as your overall, yeah.
And then you find the angle.
Should be
No.
tangent.
Oh,
Opposite over adjacent.
which is just 1/1.
No.
did you get 168?
No, Mia. they aren't just proportional. The force is not proportional. It's negative, charge of -2, charge of +3.
Oh, yeah, so.
So reduce it to their x and y. You would have to reduce the.
Lost what now?
You have to reduce it to your x and y coordinates.
What'd you lose, Miss Burkham?
And use that to determine the coordinates.
Okay.
It's vectors, basically. We're doing vectors again, but gravitors.
What?
We're doing electromagnetic vectors.
Oh, I'm going all the way back. Remember how to do that? 'Cause I don't remember
Oh, that's, sorry, so that's.
what I'm
So
doing.
you take the 1 over and then.
Too bad.
160, yeah.
That one was a
Oh.
train wreck, but that's
Did you say
fine.
168 or 160?
168.
160. I got 160.8.
Darn, I was
So.
found a shortcut.
Not
Tangent.
again. I'm close. Why do you keep doing this, Aaron?
Tangent of
Okay, Mia.
opposite
Aaron's
over
gonna be a
hypotenuse.
mess.
So the opposite would be 0.5.
Mia.
Not hypotenuse.
No, Mia, just stop.
You might
Stop.
pause the.
Okay, I'm just